It's all available if anyone wants to look at it, but I should warn you that I'm not actually very good at programming, which I'm a math major. I'll use that as my excuse. So I'm sure that most of you would probably be able to whip up something much better, but it's up there for what it's worth.
Well, there is also a security talk today at 6 o'clock. Which location?
It's at Sage, the 5th floor. It's on Android malware, or 4th floor, whatever. Android malware and reverse engineering exploitation. Because I guess it's an insecure operating system, so I don't know.
Yeah. Sorry this is taking so long to get started. Computers decided to not cooperate today. It'll work. It's just decided to be very slow.
Clicking at 10 times.
No whitelist on the internal developer network. One of the reasons I stopped using this
It just takes forever. If I have it open already, I'll use it. I know companies in general.
No,
We're a tech company.
Here we go.
You guys think it's funny, but my credit card number's on there, so.
Funny story.
So far, I haven't seen it.
Okay. Looks like we're ready to go. So
Okay, start.
So my name is Dan Nichols, and I've been working with Dr. Krishnamurthy on my senior research project, which is about cryptographic hash functions. And specifically, the goal of the project was to investigate the idea of provable security for cryptographic hash functions, and just sort of what it actually means for a hash function to be secure. And so to do that, we investigated one hash function in particular. And so I guess I'll begin by most of you probably know this, but I'll begin by just introducing the idea of a cryptographic hash function, which is, it's a type of mathematical function which has some special properties which allow it to be used for security purposes and authentication in electronic communications. If we call the hash function f, then we write f of m equals d, where m is the message or the input of the function, and d is the output or digest of the function. And one important thing is that the digest of the function is a binary string of a fixed length. So the input can be anything, any type of file on your computer, but the output always has a fixed length that's determined by the hash function. And this can be used for a lot of different things. So for an example, if you're designing a computer system and you want to make sure that only certain people have access to that system, one way that you could do that would be to make a list of usernames and passwords, store it on the computer's hard drive, and when someone tries to log in, you check to see if their username and password are on the list, and if they are, then you let them in. If they're not, then they don't have permission. But that would not be a very good idea, because that list of passwords is a pretty big security flaw, and if someone gets a hold of that, then they can basically do whatever they want. So with a cryptographic hash function, there's a safer way to do it, which is instead of just storing everybody's password in a file, you store the digest associated with their password, or the hashes of their passwords. And then when someone tries to log in, you compute the hash of the password that they enter, check to see if it matches one on the list, And if so, you let them in. And the reason that works is, even if someone gets a hold of that file with all of the digests, they can't actually break into the system because of some very important properties that hash functions have. So these are the three main properties that a cryptographic hash function has to have. The most important one is pre-image resistance, which basically means, given a digest D, it's very hard to find a message M such that f of m equals D. So basically, if you have the input, it's very easy to find the output, but if you have the output, it's very hard to find the input. And the other two properties, second pre-image resistance and collision resistance, are basically saying that it's very difficult to find two messages that have the same digest. That should be very hard to find. Now, if you've seen this before, if you're paying attention, you might notice there's something that's kind of missing from these definitions, which is, what does it mean for something to be very hard? And generally, it means that solving the problem would take more time and resources, which means basically money and computing power, than anyone who would want to solve it has. So, for instance, if breaking a crypto system would take every computer in the world 1,000 years, that would probably be considered secure, but the problem is that's not actually like a technical mathematical definition of security, because it depends on politics and economics and a lot of other crazy voodoo. So there's this idea of provable security, which is basically we would say a hash function is provably secure if you can prove mathematically and rigorously through like reduction that solving the problem is at least as hard as solving certain very hard mathematical problems. And most commonly used hash functions are not provably secure, mostly because they need to be very fast and very simple so they can be implemented on embedded hardware and things like that. And as a result, generally provably secure hash functions don't work quite as well for that. So one hash function that we could consider as a possible provably secure hash function is this function hamhash, which was proposed by Maike Matsuure, who is a German bachelor student, or who was at the time she wrote this, in her bachelor's thesis. So she designed this function that's based on the Hamiltonian cycle problem, which is a problem in graph theory. And she argues in her thesis that this function is provably secure. So I'm sure probably a lot of you have seen this, but the Hamiltonian cycle problem, it's a problem that basically asks, given a graph G, which is a set of nodes and a set of edges that link those nodes together, can we find a cycle in that graph which contains every node exactly once? So the idea is, can we find a set of edges so that each node is adjacent to the cycle, but no node is touched twice? And this problem is NP complete, so it's considered to be part of a class of very difficult problems. And at first glance, it certainly sounds like a decent candidate for something to use for cryptology. The function itself, hamhash, it's made up of three constituent functions, and the actual function hamhash is the composition of these functions. There's the function red, which stands for reduce or reduction, the function cyc, which stands for cycle, and the function graph, which is just graph. So basically, the output of each of these functions is the input of the next one, and together they make up hamhash. So I'm going to go into just a little bit of detail because I don't want to spend too much time, but just to sort of explain how the function works. So the first function, red, its job is basically to just truncate the message down to a fixed length, but it has to do that in such a way that's actually secure. So it can't just, lop off everything after a certain number of bits, because we want to preserve an avalanche effect in the hash function. So basically, we want even slight changes in the message to cause very big changes in the digest. So Matsuure suggests using an existing hash function, like one of the SHA functions, which would certainly be a good choice. You might wonder, well, if we're already using, like SHA-256 or something as just part of this function, what's the point of all this other stuff? And the idea is that SHA is not provably secure, and hopefully, the entire function hamhash, of which SHA is one part, would actually have provable security. So that would be the idea of, even though we already have a secure function, using an even more complicated one. So the output, this fixed string of length, this fixed string m prime of length L, that becomes the input of the function cyc. And cyc is basically a one-to-one mapping between binary strings of length L and permutations on a set of n objects. So basically this function is designed to associate with each possible binary string a permutation. And that permutation is going to be a representation of a Hamiltonian cycle. So because basically a Hamiltonian cycle can be represented as a permutation on the set of the nodes in a graph. So there are, if you do the math, there's n minus 1 factorial over 2 possible permutations after you account for multiple permutations that represent the same cycle. So you have to choose n such that 2 to the L is less than or equal to n minus 1 factorial over 2. That equation basically just tells us, based on how big the output of the function red is, that determines how big the digest of the function ham hash is going to be. And then lastly, the last part of the function is graph, which takes as its input this n permutation that represents a Hamiltonian cycle, and its output is going to be the adjacency matrix of a graph G. And this is going to be the digest of the actual function. It's basically a really big graph. What graph does is it adds a bunch of random edges to this Hamiltonian cycle, which makes it basically just a really big graph. And the idea is that these random edges sort of camouflage or disguise the Hamiltonian cycle, and they make it hopefully very hard to find. So this is sort of like an obscuring step that hides the actual Hamiltonian cycle. And here's just a little diagram to sort of show how the whole function works and what the steps are. And basically, you know, we take the string, we truncate it in a way that's cryptographically secure. We associate it with an n permutation, which represents a Hamiltonian cycle, and then we add a bunch of random edges to get a giant graph. And that's basically how this whole thing works. Now, it's a little bit different from a normal hash function in that it's non-deterministic, because the idea is that in graph, we add a bunch of random edges. You won't get the same random edges each time. So if you want to authenticate something and you want to determine, given a digest, is that the digest that corresponds to this message, what you would do is you use the functions read and cyc to calculate a Hamiltonian cycle associated with the message, and you check to see if that is present in the graph that is the digest. So it's a little bit more complicated, but it works in a similar way. Now the question is, how secure is this? Is it actually secure? And Massiere argues that ham hash is provably secure because finding a pre-image for a given digest graph G requires finding a Hamiltonian cycle in G, which is, it's NP complete, it's considered to be very hard, and therefore breaking ham hash is at least as difficult as the Hamiltonian cycle problem. But the problem is that the Hamiltonian cycle problem, while it is theoretically very hard in the worst case, in reality it's almost never very difficult. Almost all instances of it can be solved very quickly given the right algorithm. And it's kind of similar to the subset sum problem, the knapsack problem, which you may have heard of, which is another combinatorial problem which ended up being not very suitable for crypto systems because, you know, it's hard in the worst case, but in the average case it's actually not that hard at all. So we did a little bit of empirical testing just to sort of verify this. We generated a bunch of random graphs that were designed to be of the type that would be produced by ham hash. So they're basically a big Hamiltonian cycle disguised by adding a bunch of random edges. And then we ran a heuristic algorithm. It's based on one that was proposed in the 80s by Boyobas, Fenner, and Fries. And then it was modified to be more efficient by a guy named Kedar, and finally implemented in C++ by Gabriel Navash. So we tested this out for graphs of a bunch of different sizes and edge densities, just to see how successful it would be. And what we found was that it was nearly always successful in finding a Hamiltonian cycle very quickly. It only failed for some very sparse graphs, which is what you would expect for a heuristic algorithm. And even in those cases, basically, if it's sparse enough that the heuristic algorithm fails, then you could just use like a regular deterministic backtracking algorithm, and it would work fast enough that you could find a solution in that case. So basically, for just about any like size or density of graph, you can find a Hamiltonian cycle quickly enough. And so here's just a look at our data. On the y-axis, we have the running time in microseconds, On the x-axis is the size of the graph n, the number of vertices, and the different data series represent different edge densities. So basically we tested 7 graph sizes, and in each of those sizes we tested 5 edge densities. And if you look at the graph, you can see pretty clearly a polynomial relation between the running time and the size of the graph for any given edge density. And in fact, if you do a curve fitting, you can find a cubic function which fits it basically perfectly, which matches up with the expected running time of the algorithm, which is cubic in n. So that's basically just to show that it's not, in fact, all that difficult to find a Hamiltonian cycle in these types of graphs. So the conclusions are basically, in practice, if you're given a digest graph G, it's very easy to find some Hamiltonian cycle in that graph, and therefore it's pretty easy to determine one possible output of the function red. So ham hash we probably consider not to be suitable for practical use, not because the whole thing is cryptographically insecure, but rather because basically all of this other stuff that's layered on top of the regular hash function in red, like SHA, ends up being useless. The whole function, the pre-image resistance of the whole function is entirely dependent on the pre-image resistance of red. So there basically just isn't any point in using any of this other stuff. All that it really does is make your digest really, really huge and kind of impractical. For instance, you can see we tested graphs of 600 nodes, but I think for a graph of 600 nodes, the digest of the hash function ends up being like, I don't know, it ends up being like several kilobytes or something. It's pretty huge compared to just about any practically used hash function. So it's possible that there could be some other hash function based on the Hamiltonian cycle problem. Like maybe it's possible to find specific cases of the problem and use those, but it seems kind of unlikely. It seems like based on the research that we've read, it seems like based on any specific type of graph, you can tailor an algorithm to quickly find a Hamiltonian cycle in it. And what this really goes to show is just that it's harder than it looks to design a provably secure hash function, because you need to make sure that it's hard actually in practice in the average case rather than just theoretically in the worst case. And I guess that's it. Thanks very much for your attention.